once the density of states is known, we will look at the behaviors of electrons in these states. Now assume that you are looking at an energy band with uniformly distributed states, which is partially filled with electrons inside a box. Without the supply of energy, like at absolute zero temperature, all electrons will stay at the lowest energy state. With energy supplied by the surrounding, like placing it at room temperature, it is similar to shaking the box, and the electrons will jump around and occupy higher energy states. The distribution of carriers in the states of a band is governed by a probability function called the Fermi-Dirac distribution function. And the Fermi-Dirac function is given by the expression shown here. The function describes the probability of a state at the energy level E being filled by an electron. In the equations, EF is a reference energy called the Fermi energy level, or simply Fermi level, which will be discussed later. You may just consider it as a constant for the time being. T is the absolute temperature in Kelvin, and K is the Boltzmann constant with a value of 1.38 times 10 to the power minus 23 joule per Kelvin, or 8.62 times 10 to the power minus 5 eV per Kelvin. Let's spend some time to study the behavior of the Fermi-Dirac function. For example, at absolute zero temperature, all the electrons stay at the lowest energy state. So, below a certain energy that we refer to as the Fermi level, all the states are filled. Hence, the probability for a state below the Fermi level to be filled is equal to 1, and the probability of a state above the Fermi level to be filled is 0. Therefore, the output of the Fermi-Dirac function is expected to be an abrupt function as shown in the figure here, or you can simply plot it using Excel. Mathematically, consider that t is very close to 0. The value of E minus EF over KT becomes a very large negative number when E is just slightly smaller than EF, because it is divided by a very small denominator. The part exponential E minus EF over KT then becomes very close to 0. The Fermi-Dirac functions will give a value of 1. When E is just slightly above EF, E minus EF over KT becomes a very large positive number due to the small denominator KT. The denominator of the Fermi-Dirac function becomes infinity, and it gives a value of 0. It agrees with what we discussed earlier. At a temperature above 0 K, the transition of the Fermi-Dirac functions from 1 to 0 is smoothed out, and the probability that carriers stay above the Fermi level increases. With this property, the Fermi level can then be defined as the energy where the probability of finding an electron in a state is equal to 1/2. For a material with a band gap, the Fermi level is located somewhere in the middle of the band gap due to the symmetry of the probability distribution. That is, the probability of finding an electron in the conduction band should be equal to the probability of finding a hole in the valence band. It is because when an electron enters the conduction band, a hole will also be created in the valence band. At 0 K, all electrons stay below EF, or EV as there are no states in the band gap. Above 0 K, electrons have a finite probability of staying in the conduction band. In the valence band, we are more interested in finding the number of holes. It is more convenient to count the number of holes if the Fermi-Dirac function for holes is defined. It is given by 1 minus the probability of finding an electron in a state at a particular energy. Or more conveniently, it can be expressed in the form shown here. Generally, we use the symbol Fe of E to denote the Fermi-Dirac functions for electrons, and Fh of E to denote the Fermi-Dirac functions for holes.